So good morning, everybody. It's 11:10. Another nice day in Toronto here. Welcome. Let me just get my slides up. Oh. Hold on a second here. I'm screen sharing trouble. Hold on a sec. Let me try that again. Not working. Hold on, I've got having a PowerPoint issue, so please bear with me. Slideshow. It's sending the slides to the wrong screen. There we go. Okay. Thanks for your patience. Should have tested that before. Let's try again. Okay. So hopefully you can all see it now. I'll go back to the chat window. Again, sorry, sometimes there's a lot of pauses while everyone sits and waits for Harlow to figure out his technology. Okay, so today we're continuing on with chapter 3. We are going to finish up, we're going to talk about Newton's second law. I've got a little demonstration for that. Doing gravity, drawing force diagrams, solving dynamics problems. So we're really getting quite a ways through chapter 3 now. So let's also go to see that chat. Okay. Maybe I'll find it here. Not seeing it. Okay. So let's go to the next slide. Let's review Newton's second law and start with a little poll here. So Newton's second law stated that acceleration was the net force, which is the sum of all the forces on an object, divided by its mass. So I want to think today about what that means and how, with an equal force, how changing the mass changes the motion of an object. So I'm going to do 2 quick polls for you. The first one is you got 2 carts at rest. One of them has a lot of mass sitting on it. You put an equal positive force to the right on both of them, maybe by turning on a fan. Over the same amount of time, which cart travels farther, the less massive cart or the more massive cart? A, the less massive cart goes farther, B, the more massive cart goes farther, or B, both will travel the same distance in the same time. So let's do a prediction, and then there's another question, and then we'll actually test these out before I talk about the right answers. Let's also see if I can find the chat window here. Okay, let's end that polling and see what people are saying. Most people are saying that the less massive cart will go farther when it's when the same force is applied to it. So I think that sort of makes sense to me, because if it's more massive, the mass is on the bottom here, so the acceleration should be less. Let's go to the next poll. Oh, there's the chat. As soon as I get my Zoom all set up, we're going to be going to a demo. I'm going to have to do it all over again. Next question. 2 carts are moving at the same positive initial velocity to the right, but one has a lot of mass on it. So again, one is loaded up with mass. Then an equal negative force is applied to both carts. So over the same amount of time, which cart travels farther? A, the less massive cart, or B, the more massive cart? This one we're definitely going to have to test it out. I'd like to see what your prediction is. Michelle asked, are we going to talk about the question posted at the end of last lecture? Yes, we will. On the plan, let's give another 5-10 seconds just to, what do you think? Which is going to travel farther, the less massive or the more massive, when you've got the fan blowing against its motion? 3, 2, 1. So of the people who voted, more people are voting for the more massive cart. Sort of like 47% say the more massive cart goes farther, 40% say the less massive cart goes farther. So I think we should try this and then we'll kind of discuss it. Once again, I'm gonna have to set this up again in a minute, but here I am. So I've got a demo set up over here. Same sort of thing with the cart. I'm gonna change my mic to be the webcam so you can get it on there. Okay, so we have two carts and we have two fans on them, and we can test them out by turning them on. They go almost together. I was testing out with the same mass just to see if the battery power was the same. But now I'm going to add a mass. We'll add mass to the front one. So another kilogram is on that cart. We're going to release them both from rest now. This is that first question. So you can see when you've got that positive force on it, if the mass is more, then the acceleration is less, so it speeds up less quickly. Okay, so the mass is what's slowing it down. But there's another thing that I thought about is maybe the friction is greater when you've got more mass sitting on it. So one way we could test that, let's turn it around and have these things slowing down and then start them with the same initial velocity. So I'm going to put the more massive one there. I'm going to push them along at sort of walking speed, I guess, and let them both go. Did you see that? So actually the one with more mass on it went farther. It's got more inertia to it. Because this is not a friction issue at all. Okay, and the way I like to think of that is that if a big locomotive train is coming towards you, it requires a lot of force to slow it down because it's got a lot of its own mass and its inertia, which makes it want to continue going at a constant velocity. And now you've got an acceleration in the negative direction, which isn't as effective on the more massive cart. So if you answered B for that second one, you were right. That's good. Okay. Oops. Once again, got to fuss with my screen share here. And find all my windows again. So participants, Q&A. And chat. Okay, I'm seeing it all. So let's actually go through this a little bit more carefully. So we tried it. Now let's try to solve this as a dynamics problem. So let's just say you have a cart. Let's just look at one cart with a mass m, and there's a constant force, positive force F on it in the plus x direction. how far does it travel in the time t? So we can actually work this out. Let's do a little sketch and translate. You've got here your cart, which looks like this. It's got some mass m. There's a forward force applied on it. Its v initial equals 0. And we can call this the plus x axis right here in that direction. And so the question is, how far in time t is the question mark. Do we have to do any simplifications, make a little force diagram? I would say we're going to neglect friction and try to work this out. There will be a little friction on the actual cart, but let's neglect it for now. So what you've got for your force diagram, you've got F normal acting up and F gravity acting down from gravity, and you've got this force F acting in this plus X direction. So the F normal and F gravity cancel since there is no y acceleration. There is no vertical acceleration. That's that idea. And so the whole sum of all the forces is going to be equal to F in plus X direction. And so now we can do some of the math, represent mathematically. We're going to say that you're going to use Newton's second law, obviously. That's what this is about, which is that the acceleration is equal to the sum of the forces divided by the mass. We can maybe use x is equal to x0 plus v0 t plus 1/2 a t squared. Set x0 equals 0. We know that v0 equals 0. That's known because it starts from rest. So then you've just got, let's solve it out. Evaluate. I'm going to say that x is equal to 1/2 times f over m times t squared. So x equals f t squared, rearranging it a little bit, over 2m. So, oops, so what should say m? So the lower mass, higher m, higher x. Lower m, higher x. So less massive cart, because it's on the bottom, goes farther for the same amount of time. Makes sense. It's accelerating less. And then the next question, and then I'll get to some of your questions, is a cart of mass m. It is moving at an initial positive velocity v0 in the plus x direction, and then you've got a negative force applied to it. So how far does it travel in that time? So again, we can sketch it. There's the cart. There's your negative force. There's your positive v0. Here's the x-axis. Again, how far does it go? The diagram, the force diagram, it again sort of looks the same. You've got the normal force, F normal, going up, the gravity going down, and then you've got this backwards force F in the negative x direction. So you would say here that the sum of forces in the x direction is negative F. Okay, so F is a positive number. And I'm saying that there's a negative x direction. So negative 1 times that positive number is the x forces. So mathematically, that's when you write out your Newton's second law. A sub x is equal to the sum of the F forces divided by m. Again, we're going to use that x equals x0 plus v0t plus 1/2 a sub x times t squared. We're going to set x equals 0, but in this case, v0 is not 0. And then let's solve it. Basically, you have x is equal to v0 times t minus f times t squared over 2m. So what this means, v0 times t, which is larger than this next term, is the same for different mass carts. Doesn't matter what the mass of the cart is. V0t is sort of that initial velocity momentum, different mass carts. But what happens here is that more massive cart means that ft squared over 2m is less. So negative ft squared over 2m is less negative. So x is higher. It's a bit complicated there. But again, the idea is that the more massive cart has a smaller negative acceleration. So it has more of its own inertia and goes farther. So thanks for your patience with that. Let me see if people have some questions. Victor, you've had your hand up for a while. I don't know if you remember raising it, but do you have a question?
No, sorry, I just accidentally left it on. My bad.
Yeah, you got a lower hand. I noticed that it's been up for a while. Hamad, do you have a question?
Yeah, so Professor, you know the equation x is equal to x initial plus v times change in t, that equation? So
Yep.
x represents the final displacement, right?
Exactly.
So why would you need to write x naught when the displacement is always like from the initial to the final?
Yeah, that's a good question. So actually, it's not that the x is the final displacement, x is the final position. And so, yeah, you're right. If you write like delta x, it would just be equal to v naught t plus 1/2 at squared, and you wouldn't have to put that x sub 0. So if x is just the final position, then you have to start from the initial position. So that's a really good point. Another question, I have time for Siddharth.
Hey, Professor, can you hear me?
Yeah, I can.
Yeah, so I just had a question about a question like this, for example. So when it says how far does it travel in time, are we good with just leaving the simplified formula there? Or do we need to write the paragraph where we explain like what would happen with the equation depending on what values are actually there? Because we don't have any values in this question.
Yeah, exactly. That's a really good question. And so what happens a lot is the question is sort of, you know, what's the answer? Well, the solution to the answer is just, I can put a box around it. Oops. I can put a box around this. X equals that. That is how far it travels in time t. But then I think what this step is down here, this whole paragraph, what I'm doing is I'm sort of evaluating the answer. And so this is a little bit of, it's a bit subjective. Different people will evaluate this differently, but what I was thinking is how, for a constant force, because I'm thinking back about that demonstration, same fan on both carts, constant force, if you adjust the mass, how does it adjust the distance? And it wasn't really asked in the question, but it just sort of putting that as an extra evaluate. But the solution is just that equation. They're all good questions.
Thank you.
Yeah, sure. Right. So good. So, can I go slower, please? Yes, I should try to talk slower. I tend to get a little excited during these things. Okay. So, the next step in chapter 3 is Newton's third law. And it's the equal, every action has an equal and opposite reaction. That's that kind of thing. So, and the way it's stated in a Kinetic, which is a little bit better, is to say that when two objects interact, Object 1 exerts a force on object 2. Object 2, in turn, exerts an equal magnitude oppositely directed force on object 1. So you can write this as a vector equation. F1 on 2 with a little vector sign on top of it equals negative F2 on 1. So if the diving board, if this is object 1 is the diver and object 2 is the diving board, then this force right here is the force of 2 on 1 in that direction. There's an equal and opposite force. You draw in a different place, but the magnitude of that vector is the same, and the direction of that vector is exactly opposite. This is F of the diver 1 on the diving board 2. F1 on 2. So, example, if you hit a nail with a hammer, this is the force of the hammer on the nail, F(H) on N or something, hammer on nail. There's an equal and opposite force hitting the hammer, the nail hitting the hammer, F nail on hammer. Okay, there's lots of examples of that. So let's think about a truck which is pushing a car up an incline with some acceleration. And what I'm imagining in my head is that someone's car is broken down and it's not really working anymore, but they've got it neutral, so it's rolling. And the truck is trying to help them by pushing them up the hill. So, and the question is, and so they're accelerating up the hill. The question for you is, which is larger, the magnitude of the force that the force of the truck applies on the car, or the magnitude of the force that the car applies on the truck? So, and the options are A, the magnitude of the force, the magnitude of the force the truck applies to the car is larger. B is the magnitude of the force that the car applies to the truck is larger. C, the magnitude of the two forces is the same. D, you would have to know the angle theta to answer this question. Or E, we must know the masses of the truck and car in order to answer this question. We're doing okay for time. Okay. Great question. Is Newton's third law only applicable to inertial reference frames? That's from April U. I think that might be the case where you can always apply Newton's third law. But let me just end this polling. Most people are saying, I think what I was sort of thinking is that the magnitude, this is Newton's third law, and it does apply. Now, I'm actually thinking of this in an inertial reference frame, which is the lab. There was a force on car 2. There's a backwards force on the truck. So if this is 1 and 2, they're equal and opposite. And one of the ways I like to think about this is I imagine that there's a compressed spring between the truck and the car. And this is an accelerating reference frame, I guess. So I would imagine that the spring itself has negligible mass, so it doesn't need a net force on it. The spring is compressed and it's symmetric. The spring doesn't really know which side of it is which, you know what I mean? So the fact that it's compressed is going to push equally in both directions, equally on the car and equally on the truck. So that's how I kind of conceptualize Newton's third law in my mind. It shouldn't matter whether you're the car or the truck. So the question is, why do they accelerate up the hill? And that we're going to come to later. And we're going to have to actually solve out not just Newton's third law, but also Newton's second law. But let's continue with this for a bit. Forces always come in pairs. Every force interaction always involves two objects and two forces. These forces are equal in strength and opposite in direction, and they're always the same kind of force. So gravity, gravity, normal, normal, friction, friction, tension, tension. Let's ask this question. a Mack truck, which is one of these great big dump trucks or something, drives north on the highway, maybe at 120 kilometers per hour. And it's barreling along, and it has a head-on collision with a mosquito that's heading south. So which is true? It's logical. Is it that A, the Mack truck does more damage to the mosquito than the mosquito does to the Mack truck? B, the mosquito does more damage to the Mack truck than the Mack truck does to the mosquito? C, the Mack truck does the same amount of damage to the mosquito as the mosquito did to the Mack truck? D, it's impossible to determine without knowing the speeds of the truck and the mosquito. I never told you the speed of the mosquito. Or, I guess E. None of the above, I guess. Yeah, a few minutes to think about this. A few seconds. Okay, guys. Well, this is the strangest poll I've seen. Let me just end it and I'll show you what people are thinking here. So I guess because of Newton's third law, looks like 45% of you are thinking that this mosquito and the Mack truck experienced the same amount of damage. So now I don't know exactly what you were thinking, but in like amount of damage, what I kind of meant there is, you know, how much it was, the object got changed as a result of the collision, right? So, you know, example would be, you know, the mosquito gets killed and completely splattered on the windshield and is changed from a flying mosquito to just a smear of biological matter on the dirt. That's a lot of damage, okay? The mosquito's family is basically applying for life insurance benefits and that kind of stuff. Like the mosquito is dead. Whereas the Mack truck, his coffee could be sitting there and doesn't even rattle around, right? Like the Mack truck just keeps on driving. So I would say that 100% the mosquito received a lot more damage. So it's the difference between, I guess, force and damage. A equals F over M, F equals MA. If the force is equal on the truck and the mosquito, is the acceleration equal? Acceleration is higher if the mass is lower. So the mosquito reverses its velocity and accelerates quite a lot, and maybe at even more than 9.8 meters per second squared. It might suddenly have 1,000 meters per second squared, and due to that large acceleration, it ends up getting quite damaged. The mosquito accelerates more, so it receives more damage. That's sort of what I was thinking there. Wouldn't the mosquito get repelled due to the airflow as the truck is moving? Yeah, I guess so. I do think that some mosquitoes must hit some trucks, though. If the mosquito is going very, very fast. D. Someone said, could it not be D if mosquitoes moving very fast? Once again, I just don't think yeah, I guess maybe a mosquito going fast, like at the speed of light, might put some damage on the truck, but I don't know if that's really what I meant there. Can you imagine like a really high energy mosquito? Okay. So last time I asked, when you pull a wagon, Newton's third law states that the wagon pulls back on you with an opposite force. And this actually, I'm going to turn the light. We're running in a circle. The old joke goes something like, okay, a farmer has a donkey, and the donkey, you know, pulls this wagon across the field every morning. But then the donkey goes and takes physics 131 and learns Newton's third law, which is every force has an equal and opposite force. And so one morning, the donkey gets up and just stands there. And the farmer says, why aren't you pulling the wagon like you always do? And the donkey says, I'm not going to. If I pull forward on this wagon, the wagon will pull backwards on me with an equal and opposite force, and we won't be able to go anywhere. So what is the answer to that? How do you solve this conundrum? Because that actually is a kind of a difficult one. The way I solve it is I remember, okay, so actually the first sentence is correct. When the donkey says, when I pull forward on the wagon pulls backwards on me with an equal and opposite force. That is correct. That is Newton's third law. However, when you say these forces should cancel each other, that's not correct. The force that's pulling backwards on the donkey from the wagon, that pulls on the donkey. Whereas the force that the donkey pulls on the wagon, that's pulling on the wagon. So those are on two different objects. They should go on two different force diagrams, and they can't cancel each other out. So the way you solve this is there's an entire third object here, which you're not thinking about, which is the ground. Okay, the ground is involved. And the forward static friction on the bottom of the donkey's feet is pushing forward on the donkey. And the backward friction that's slowing down the wagon is pulling backwards on the wagon, but it's less than the forward friction on the donkey. And that's why the whole system can accelerate along. Okay. So that's how you sort of resolve this. And in fact, if you think about it, if the donkey was way out in space and there was no earth and there was no ground, then it is true. It doesn't matter what the donkey does, he can't accelerate the wagon. So hopefully that helps a bit. Let's talk a little bit about these interaction forces. If you have an accelerating car, what's the car-earth friction interaction? Well, the car's tires rotate around the back. If it's back rear-wheel drive, then this tire is forced by the torque of the engine to accelerate around in a, I guess, counterclockwise direction. That pushes backwards on the ground with static friction. So therefore, the earth as an interaction reaction is pushing forward on the tire with an equal and opposite force. And that force, since it's connected to the tire and the object of the car, that's what pushes the entire car forward. I bet you never thought about all those things happening. When you press your gas on the car, it rotates the wheel of the car pushes backwards on the ground, and then the ground pushes forwards on the wheel, and then the whole wheel pushes the car forward. That's how you accelerate a car. A couple more of those. You can have this with rockets, okay? So a rocket accelerating upwards, the rocket pushes downward on the accelerating gas. That's a pressure force. So the expelled gas pushes upward on the rocket. And this can work even if the rocket is way out in space and not near any planet surface. And then this one, the basketball Earth gravity interaction. So consider a basketball that's in free fall here. So no one's touching it. Because it's flying, right? Gravity is pulling the ball down. So what is the other force in this interaction? It must be equal and opposite by Newton's third law. Is it A, the thrower's feet are pushing the ground down, or it's even his hand there. B, the ground is pushing the thrower's feet up. C, the gravity of the earth is pulling the thrower down. D, the gravity of the ball is pulling the earth up. Or E, air is pushing the ball up. It's a bit of a weird one. Only one of these really makes any sense to me at all. So I'm going to give me another 5 seconds. 4. E. Give you maybe another. Couple Okay. So I'm going to end polling. Okay. So actually the one that won is that the air is pushing the ball up. So that's not the case. What happens is that the ball is going up because of its own inertia. Someone threw that ball up, okay? And the air is not what's pushing it upwards. If you want to figure out what is Newton's third law say? When there's a gravity force pulling the ball down, what's the other interaction force in an interaction pair that's governed by Newton's third law? So this, I gotta say, is a pretty obscure little question. And the answer is that the gravity of the ball is pulling the Earth up. Now that may not make a lot of sense to you, but this idea is that this downward force is F of Earth on the ball. It's kind of silly, but imagine that you've got the Earth is pulling down on the ball is pulling up on the Earth. Well, the acceleration of the ball is this force divided by the mass of the ball. The acceleration of the Earth is that same force by Newton's third law divided by the mass of the Earth. So if the mass of the ball is equal to 0.5 kilograms, and the mass of the Earth is equal to 6 times 10 to the 24 kilograms, according to Google. And the sum of the forces is going to be Fg. It's going to be actually equal to 4.9 newtons. That's the interaction force, which is going to be the same for both. So this one is going to be equal to 4.9 newtons divided by the mass of the ball, 0.5 kilograms. Whereas this one is going to be the same 4.9 newtons pulling upwards on the Earth divided by 6 times 10 to the 24 kilograms. So this one turns out to be 9.8 meters per second squared. Oh, well, that makes sense, doesn't it? But then for the Earth, it's equal to 8 times 10 to the minus 25 meters per second squared. So at the same time as the basketball is accelerating down at 9.8, the Earth is accelerating up at 8 times 10 to the minus 25 meters per second squared, which is 0. That's why the Earth doesn't go up. It's weird, but that's the idea there. So we can move the Earth by throwing a large number of balls. Exactly. If you jump up and down, the entire Earth is going down and up underneath me. Can you feel it? No, because it's not much, right? That's the idea. I see. I have to scroll down to the bottom of this. So actually, Raveen, did you have a question? Raveen, Christian, Troy? Again, if your hand is up, that's fair game. I'm gonna, so, and Liel?
Hi, can you hear me?
Yes, I can now.
I was wondering if maybe after you finish the lecture, could you go over again creating the system of equations for like the water balloon problem? Because I'm just a bit confused on how to find like the common variable to connect like the two equations.
Yeah. Sure, yeah, I mean, that's a good office hour question or something you could ask your TA to go over during practicals or something like that. But yeah, definitely. And then Rohit, did you want to unmute?
Hi, can you hear me?
Hi.
Yeah, so going back to the car-earth friction interaction, how come it's static friction that acts on the
yeah, we're going to get more into that, but the idea is that so kinetic friction is when the two surfaces are sliding relative to another. So if you like are going along and you slam on all 4 brakes at once and the car goes screech along, that's kinetic friction. Or maybe if you step on the gas so much that you hear the screeching of your tires. But under normal driving circumstances, you never hear that screeching. So actually the surface, the bottom surface of your tire is not sliding relative to the road surface. And so it turns out to just be static friction. It's called rolling without slipping. But again, that's more of a chapter 4 and chapter 5 concept, so we're not gonna, but that's a great question. Thank you. Okay. Good. It's really nice to hear from some of you so that I don't feel like I'm totally alone here in this place. Okay. What I wanted to do to go back to that whole, why does this system able to accelerate up? And we're going to talk more about static friction now. Let's draw force diagrams for the truck and the car and identify the interaction pair that links these two objects. So if I say, here's the truck, which I'm going to call T, and I'm going to do one for the car over here, which I'm going to call C. So the force diagram for the truck, so there's going to be a tipped normal force, F normal, on the truck, I guess, because it's on a tipped surface. There's going to be the downward Fe on the truck, that's the gravity force. And then there's going to be this backwards force, the force of the car on the truck, C on T. Okay, I guess that's sort of a normal force or something like that. And then there's a forward force, I believe, which is the F friction, and I think this is static friction on the truck. So all of these forces are on the truck. You can almost drop the on T because we're drawing the force diagram of the truck. And then the car, its force diagram looks like this. Again, there's this F normal on the car. There's going to be the force of gravity on the car. I'm going to call it E on car to kind of use the same notation as your book. And then there's this force of the truck on the car. And there's going to be, I think, this could be either way, but I think if the car is dead and it doesn't have an engine on, then there's going to be a force friction backwards on the car. It could be forward or backwards, actually, on the car. It'll be backwards. And we'll talk again more about that a little bit later. So the whole idea here is that it says identify the interaction pair. The interaction pair is this force and this force. These ones are necessarily equal and opposite by Newton's third law. The force of the truck on the car is equal and opposite to the force of the car on the truck, okay? And then this one right here, static friction, propels the system forward. So it's going to turn out that the thing that's getting these things to accelerate up the hill is this external force of the friction of the road on the truck. And that's not too easy. Okay. I might have a little too much on my plate here. Let's do just one more poll question, and I'll work this one out. Okay, the figure shows two blocks with two forces acting on the pair. So someone's pushing to the right on this 1 kilogram with 5 newtons, someone's pushing to the left with 3 newtons. The net force on the larger block is A, less than 2 newtons, B equal to 2 newtons, or C greater than 2 newtons. Let's think about this one. I guess it's the magnitude of the net force is less than, equal to, or greater than, I should say. So take a stab at this. You can try to guess based on your intuition. And then I think I should just try to work it out because we have a little bit of time. So 5, 4, 3, 2, 1. So 84% of you have voted. So most people are going for equal to 2 newtons. And in fact, I think the net force on this whole system of both blocks is going to be 2 newtons. But then the question was, what is it just on the 3 kilogram block? So the way I would do this is I would split this problem into sort of 2 halves. I would say, first, consider the system to be both blocks. Okay, and so what we're going to do is we're going to define plus x to be in this direction towards the right. We can draw our little dashed line around that. So the m of the system is equal to 1 kilogram plus 3 kilograms equals 4 kilograms. And we're going to find the a. And so you can try to draw what the forces are. There's normal, there's gravity, those are going to cancel. And then you've got the 5 Newton force acting from the left to the right, and the 3 Newton force acting from right to left. So when you draw a force diagram, you draw all the arrows as emanating from the dot at the middle. So they kind of end up flipping sides there. But anyway, the point is that the net force in the y direction, we could put y to be up, and the y is equal to 0. Okay, so no y acceleration, sort of a constraint. But the interesting thing is that the forces in the x direction is equal to plus 5 minus 3 equals plus 2 newtons. And so the acceleration in the x direction is going to be, by Newton's second law, is going to be 2 divided by 4 kilograms. So it's going to be 0.5 meters per second squared. And then what you do, second, consider the larger block as the system. Because that's what you're asked about, is what's the net force on the larger block. And what you know, that acceleration is equal to plus 0.5 meters per second squared. Since the whole system is accelerating towards the right with acceleration of 0.5 meters per second squared, then that applies to all the objects in the system, including the larger block. And now you can solve A is equal to the net force divided by m for F, for net force. And you get F equals ma. So in this case, it's going to be the mass of the larger block. It's going to be just the 3 kilograms times the 0.5 meters per second squared. And what you get is that net force is equal to 1.5 newtons. I'm going to space a bit there. So that's A. So another way of looking at that is that you do have a 3 Newton force here, and you have a 5 Newton force pressing on the 1 kilogram block. But some of that 5 newtons from that side gets taken up by actually accelerating the 1 kilogram block. So the 1 kilogram block only pushes on this side with like less than that. Maybe it's like 4.5 or something. Must be 4.5 newtons. And so the net force on that 3 kilogram block is going to be the 4.5 minus the 3, and you're going to get 1.5. Yeah. So I'm going to actually skip this one. We're going to do this. I have a problem that was in your notes. I'm going to do next time. So I do want you to finish up chapter 3 because we have a test on it, and then on Tuesday night. And something to consider. So after having been thrown upward, apple, an angry bird. A 100-gram apple falls back into your hand and you catch it. While you're catching it, is the force that you exert on the apple more than, less than, or the same as the force that you exert on the apple when you're just holding it at rest? You're catching versus holding it at rest. Talk about that next time. It's a little bit more of a review. And I think what I'm going to do is say thank you. I'm going to turn off the recording and I'm going to go to the questions for the hands that are in the air in order. So just do that.